Okay. As we mentioned before, that those codes, the makeup codes, we will introduce a population-based model in such a way that you don't need the people who don't come to attend the makeup course doesn't need to be worried about those materials because it will not be in the final exam. Okay, we are not. Okay. But before we start to take a look at some videos that introduce the population-based model, we'd better have some basic understanding. And also, those understanding will motivate you to learn this model. Okay. So here I will give you the most famous application of the population-based model. I don't know how many of you know that the pharmaceutical industry required a process of crystallization. So they get a drug. Nevertheless, this drug cannot be sold to you in liquid form. Usually when you go to the drugstore, you get a drug is solid, right? It's like a tablet or a capsule. And but inside that tablet or inside that capsule, the drug needs certain morphology, okay? So here, it shows two extreme conditions. The left-hand side, as you can see that it is a needle shape. In this shape, the dissolving curve will not fit the design. So they try to recrystallize those drugs, okay, or those morphology. And it need to be made into a specific shape. Probably I can show you one. Yeah, this one. This one probably a better one here. Okay. So you go to drugstore, you see the drug is in this way. Nevertheless, when you grind it into a powder, before you do that, you need to make sure the shape is correct. If the shape is not correct, as you can see here, it has a shape like a wheel, a wire, or a rod, or a dot. And all those shapes, it actually has different behavior. So it needs to make the shape into the correct morphology. Okay? You get the idea, right? Okay. I kind of believe you get the idea. And the population-based model is a model created by the chemical engineer, especially by my advisor, Ren Krishna. And this is the only book of the population-based model, and he published in 2000. It doesn't mean that this field is small. It's not, okay? Many people are involved in this field. When I was a grad student, I attended a conference. The conference size is about 200 people. So it's not too small. It's not a very big field, but it's not too small. And this book is specifically, yeah, let me use the other one. Okay, good. This book is specifically introduced the background and the fundamental idea of the population-based model. But it doesn't mean that this is an easy book. It has many introduction. Sorry, I shouldn't say that. It has many content introducing the theory of the population-based model. So it started from the probability distribution. And all those knowledge that, as I know, you can only find in this book. And if you type population balance, of course you will find many other books. But only this one, it gives you the origin of the population balance model. And in that way, it also gives you the confidence that the model is correct, okay? Nevertheless, if you just want to use the model, you probably only need 2 chapters of this book, chapter 1 and chapter 2. Probably chapter 3, yeah, at most, you should be able to use the model, okay? Yeah, okay. And the model, they try to do something is they like the fluid mechanics. As I say that in the fluid mechanics, if you move from one point to the other point, so in this model, the fluid mechanics, if you have a droplet and you move to here, like we usually say that from the position 4 to 5, then you treat that this is a movement in the real axis in the real world. But in population balance model, you can treat for example, this one here has actually 3. If you want to describe this one, you will describe in this way. So you have right, and then for each length or each dimension, you apply the idea of this. So in fluid mechanics, it moves from one position to the other position. But in population balance model, it does not move. Nevertheless, it can grow or shrink. But you describe that behavior.
Hi guys, welcome to my channel. My name is Joseph. So in this particular video here, I'm going to give you an overview of what population balance is. Let's jump straight into this video. So in real life, many quantities are being distributed. For example, they will be distributed in size. If you look at a bunch of particles here, right, and if you actually sample this particle here, right, if you sample this particle here and you actually go and count the number of particles for a particular size of the particle, you'll be able to actually build a distribution curve that looks probably like this. So let's just call this distribution the number density, right? Let's just call this the number density. So let's say
Okay, let me introduce the idea, the number density. Many people who don't realize that, so they have some trouble when they try to apply a population-based model. So you see a distribution. And then in population-based model, we usually use F to describe that. But it doesn't matter. You can use any notation you want. And then we call it a number density. But in your mind, you may feel something is. So this x you can think about. Sorry, this x you can think about is this one, this h. So the number density describe that at a different h, how many particles you have. All right, you get the idea. At a different h, how many particles you have. Nevertheless, it's different from the probability density function. How many of you know the probability density function? Please raise your hand. Come on, how can you guys don't know that? How many of you don't know the population based? How many of you don't know the probability density function? One? One don't know. No one want to answer that. Okay. Anyway, I will introduce that. So let's use a die, okay? Even high school student can answer it, so you definitely can answer it. If we roll die, that is fair. It has 6 faces, right? So what's the probability of getting one? Yeah. He is correct, right? Kind of easy. This one, right? 1/6. Then the difference between probability density function and number density is number density. After you normalize the number density, you get a probability density function. So what's that mean? It means for number density, it's more like you don't know this at the beginning. So you try to roll a die, and then you roll a lot of, for example, you roll a die 6,000 times, and finally you get each of that in F. For example, 1, you get 1,000, right? Because this one multiple this, you get 1,000. So the number density is defined this way. Let me say again. Okay? The number density is different from the probability density function. The number density try to describe the times you did in the system. For example, you roll 6,000 times. Then the number density of if is fair, okay? The number density for the first position is 1,000 because you rolled 6,000 times. And if you roll more times, for example, you roll 12,000 times, then this one may become 2,000. So if you normalize the number density, you get a probability density function. All right? That's the basic idea. Because this one is the function that will continually appear in the population-based model, so I better introduce that. Well, since it's already 8:10, let's move back to our original course, and that makeup course continued in next week, right? All right. Okay, let's come back to here. We have this interesting things here, right? This one. So last week we tried to derive the equation of continuity. So what we want to do is this one. Yeah. How about I just delete these two? Okay. It does not become bigger. So last week we tried to derive this one, right? And then we give you a balanced question. This one I can give you much more points, okay? We give you a balanced question asking about if this equal to 0. If this equals 0, the fluid is incompressible fluid or not? Or the question is actually, let me remember that question. Okay, the question is, for an incompressible fluid, will this one equal to 0, right? Okay, so anyone have an answer? Yeah. you feel is 0, you also. So how about we do a survey here? I really want to know where I can get the noise, so I can avoid that. Equal to 0. How many of you feel it's not equal to 0? So let's do a survey. How many of you feel it's 0? You too? 14 people. How many of you feel that for the incompressible fluid, it does not necessary to be 0? No one? No one? Okay, all right. Okay, 0. No one. All right. Let me explain this. Okay. So this equation, this thing, for the incompressible fluid, it does not necessary to be 0. Or I should say the incompressible fluid is not a sufficient condition for this one to be 0. Okay? And what you feel equal to 0, it should be the other equation, not this one. And let me try to derive that for you, okay? Well, probably I give you the answer now so you can have a better understanding of all the things. This is not 0 because this is partial derivative. And that's thinking about one condition. So, we'll draw a two. Okay, anyway, let me think in the other better way. A tube, okay, a tube. And what I want to do is we put two kinds of fluid into the tube. Okay, because I know some of you have the background of chemical engineering. So let's assume it's plug flow. Plug flow means it does not have the velocity distribution. All right? Okay for that, right? Plug flow. Okay. Velocity. Yeah, the velocity in the r direction are all the same there. Okay, so it's plug flow. Okay. So for this flow, originally we have the blue liquid, and let's make it density as 1, like water. And then the second one we have the black liquid. Let's make it density probably 0.7. And let's assume it's oil. I don't know the density of oil, okay? I just assume that. All right. And then we first have probably you will feel in the reverse way is better. Okay. Then let's flow in this way. Okay. So we first have the oil in the tube, and we assume it's plug flow, means there's no friction between the liquid and the solid. Okay. It just moves. And first we have oil, and then next we use the water, and it flow in this way. And we measure at this position here, probably here. Oh, here. Okay, here is better. I don't want to. I don't want to make a mess here. So let's measure here. It's so terrible. Sorry. Yeah, okay, good. So we measure here. All right, we measure here. And we understand that when the fluid flow, we will first measure the density as 0.7, right? And after a while, our density become 1. But both the oil and the water are incompressible fluid, and so it's not sufficient condition for partial rho partial T equal to 0. You get the idea? Or is something contradict to your understanding? Okay, you get the idea, right? And then you may have a question. Then it seems something wrong there, because in your undergraduate course, you clear know that if this one equal to 0, or divergence V equal to 0, you get an incompressible fluid, right? Hopefully you guys have memory about that. So you clearly have a memory about this. And then I told you there is a partial derivative. It's not the necessary condition nor the sufficient condition for the incompressible fluid. Okay? And then let's introduce these two, okay? So hopefully I can give you some insight into this very fundamental equation, the equation of continuity. But before I do that, I want to say this thing. It's actually come from a question of the student. It's not come from me. So one day a student asked me that. Say, this is the condition for the incompressible fluid. Then what's this? Since it's not a condition, then can I give him some example? So I think about that, I get this example. All right. So your question sometimes is very important, and you help others to understand the whole system. All right, let's come back to here. But before we do that, we may ask you a question. How many of you are familiar with this thing, this style? We call this style DL. So we call this style. But more important is you guys should know that this equation is called equation of continuity. Okay. It's important. It's one of the two fundamental equations in fluid mechanics. The other is equation of motion. I just did that, and we will deal with that later. Okay. So in fluid mechanics there are two equations only. One is equation of continuity. The other is equation of motion. And this one comes from mass bands. We just show you next week. Okay? And the other is comes from the force bands. All right. Let's come back here. How many of you are familiar with this deal? Come on, you guys never raise your hand. One. That's good. Huh? Yeah. Thank you. So, and the same question I will ask: how many of you are not familiar with this? No one. Anyway, I still want to introduce that. You can. You can treat this in an engineering way. Okay, it's not a correct way, but you can treat that in an engineering way. This one, in mathematics, we usually call this an operator. An operator means it's something operator on a function, or usually we call it functional. But it's okay. You don't want to get involved in that. What I want to say is, if you don't treat this notation as an operator, you may treat that something like a. An operator in this way. And if you don't know what's the operator, it's okay. You just treat that as something like a function. And if you do this to the vector, and then for this one, although you know this is an operator, and you know this del with the dot is one operator, and usually you call it divergent. But if you don't want to get involved in the operator, you just treat that as something like a vector. Then you just do the dot product. So you have this one multiplied by this, and this multiplied by this multiplied by that. Then that gives you. Hopefully you get an idea. Okay. After we introduce that, I want to say something about this one here. This one here. So let me erase the rest, and then we will have this one. Okay. And probably this one also. Oh. You only have a very small amount of battery. Usually I can only use this to talk about 5 minutes. So I think I can only use this one. I don't know if I can use microphone. Next time maybe I'll. But note that we actually have this one here, right? This one here. And it has this one. This one is different from this one, right? So we have this one. Just as you know that I like to give the balance points. So from this one, how we get this one? Connect to this one, the divergent V. Yeah. You want to write it down? Write it down, please. Thank you very much. Okay, thank you. You are correct. It's kind of easy to get these balance points, okay? But I really appreciate his help. So he easily get this answer. But if I ask you why you will get this answer, you may have some difficulty to reply that, right? Or anyone who say that how you get this one, you may have some difficulty because this is what we try to teach in this course, all right? So in this course, we will teach the index notation, and use the index notation, you can easily get this too. But now you can only memorize that this thing can become this too, all right? But anyway, this is correct. So this thing can become this too. And that's why the partial derivative of rho is not a sufficient condition for incompressible fluid. Because the partial derivative equal to 0 means this whole thing equal to 0. And it does not lead to this thing equal to 0. You still have this one, right? Still have this one. All right. And now let's take a look at this one and that partial derivative and try to get this one. All right? All right. Put it in a very later chapter of this big D, but we use that all day long, okay? So every day, every class in the undergraduate course, we see this notation. Let me introduce this notation first. I don't know how many of you have memory about this one, but in undergraduate course, usually you heard shortest one. It means that I mean not this low. I mean this one. Let me look at that. Okay. Then the instructor usually told you. This one is try to describe something along with the fluid, right? Go with the fluid. Hopefully you get the idea. The concept is in this way. You have actually two coordinates. Here is S and zeta. And if you have the S coordinate, it means it's a fixed coordinate. It's called S. And the other coordinate is what they call a particle pace. It means that it flows with the fluid. All right? So you have two coordinates. One is the fixed coordinate, which is the XYZ you know. You know the XYZ, right? And you know XYZ is there, then it does not change. It's just there. Stay there. And the other is the so-called particle pace. This one will move with the fluid. And if we use this beautiful picture to illustrate that, then you can understand this way. If we sit here and we watch this thing, we are in a fixed coordinate x, right? Because we don't move, we just watch that. Nevertheless, for these two young ladies, they are in the zeta coordinate, right? Because they move with the fluid. So their coordinate continually flowed. So they move with the fluid. All right? You get the idea, right? So the first coordinate is from our side. From our view, from our view. From our view is a fixed coordinate because we don't move. We just take a look at that. And then we find the shock may just swing from one side to the other side. Okay? But from the view of these two young ladies, the shock is not just swinging from one side to the other side, but they will also see the shock. They will also feel that they pass the shock, right? Because they move from the upper stream to the downstream. So their coordinate is different from us, all right? So this is the particle coordinate, and our coordinate is the fixed coordinate. All right, and once we know these two coordinates, forget about all those things. Let's come back to, just here. Let's come back to this one. This D is actually the full derivative, okay? Don't think about that thing as something special. It's a full derivative. First is a full derivative. So let's try to describe that. Do something to this f. Let's assume that f is a function of t, x, y, and z. Think about this, okay? Think about this. If they move with the fluid, so they actually, if you want to describe some behavior of them, it's actually a function of time and position, right? Time and position. So f is a function of time and the position x, y, z. And I don't know how many of you know this one. df dt is equal to okay? And think about that. If you move with the fluid, if you just move with the fluid, okay? Just like that. What will become your dx dt? Becomes the fluid, right? So you actually get this dx. This is v1 and this is vz. And once you do it that way, you will I want to make notes, so I will wait for a few minutes to let people finish. And also, because this idea is kind of important. But if we write in this way, we automatically assume that we move with the fluid, right? So we should put the capital D here. All right? So you get the idea, right? So I give you probably a few minutes so all the people can finish your notes. And also, if you don't want to make notes, take a close look at this whole thing. This capital D bothered me for a real long time, okay? When I was an undergrad student, I feel so strange about this capital D. And because I don't understand what's the meaning of flow with the fluid. And here clearly show that it's just because your coordinates go with the fluid. So you use the Vx to replace the dx dt, and Vy to replace the dy dt, and Vg to replace the dz dt. Okay? All right. Hopefully, I still have some people try to make notes. Let me wait for probably 1 or 2 more minutes. And also, people who don't want to make notes, you may try to some people are not familiar with this, so make sure that you feel they are correct. Or I should say it is correct, okay? Well, that's good. I really appreciate his help. So great. Okay, I kind of believe I'll still have people who try to make notes. I'll wait for them. So try to have some memory about this capital D, okay? Because in fluid mechanics it appears everywhere. And you don't need to memorize that. You can just understand it by this all those equations. You should be able to understand that. I don't know what happened actually. So difficult to. Yeah, thank you. 还是会，它是因为靠它的。
对，因为它是定频的，这个是比较容易被感染。
Oh, I see. Okay, thank you. Thank you. Okay, thank you. All right, let's come back here and let's move on. So we have this one, right? So if we put a low here, we actually have probably I erase the rest, okay? Ooh. I usually put a del to indicate it's a vector. Okay, let me say that again. I usually put del, this, to indicate it's a vector. For the people who are not familiar with English. 我通常会放这个波浪形，去代表它是一个向量。那如果是张量，我可能会放2个波浪这样。那课本会用粗体字，但我没办法写粗体字哦。OK， 是。但是有时候我忘记啊，忘记就算了，好不好？你们就自己把它补上去哦。OK。So if I forget to put a del, you can put that yourself, alright? I sometimes will forget that. So this is used to indicate the vector, and if a tensor, I will use probably 2 dels or 3 dels, depends on its dimension. Okay. All right. And so if we put rho, if we replace f as by rho, then we will have this. And just as usual, I will wait for all the people finish notes and introduce that. All right. And during this time, then I should do something to help my funny microphone situation. I kind of believe if I open this, I will get a better signal. Let me try again, okay. Right. Hopefully it works, okay? Hopefully. I don't know. Let me try to open that. See if I can get a better signal. Because at the very beginning, I think it's get noise. But after I talked with the officer in our department, they say it's because the signal is not strong enough. So it's very likely if I open this, I can get a better signal. I don't know. I'll try this, okay. And also tell you one good thing, okay? So I decided to do this from this semester. So in the final exam, we'll have one question about how to derive the equation of continuity. All right? Okay. Good. You are lucky you are here, right? And then I will also ask you how to get this equation. This one. All right. Okay, let me say again because it's kind of important for you guys, right? in final exam, we will have one question about how to derive the equation of continuity, and we will not give you the equation. Okay, so try to derive that by. We will give you the control volume. All right. And once you get a control volume, you try to derive the equation of continuity by control volume. And after that, we will also ask you how to rewrite the equation of continuity in this capital D, which is this one. And then you should get your points right. I already give you the question. All right. Okay. So let's come back here. So how to get that is kind of easy, right? Because we know the definition of, not definition, we know what's the d rho dt by this one, right? Oh yeah, by the way, if you see this question in the final exam, you don't need to derive these d things, okay? You can just assume that you know the d. That should be fine, no problem. But don't assume that you already know the equation of continuity. That's not correct. That's the question itself, okay? And then you have this one. So you put a law in this position, right? Put a law in position F. So you put law in position F, right? And then you get this one, right? And also this one. And then we have this, right? This here in your PowerPoint or in our PowerPoint. So you put that minus divergent rho v here, minus divergent rho v to replace this partial derivative of the density. And you still have this term, so you put this here. And this, thanks for your classmate, give us this one, right? So you replace this by this one, And note that it has a minus side here, so you have minus this and minus this. So you have minus this and minus this. All right? And then luckily, you find out these two are the same, right? This and this. Exactly the same. Cancel out. You get this term only. Okay, this one. And I give you the idea that divergent V equal to 0 over capital D rho dt equal to 0 is the necessary and sufficient condition for incompressible fluid. Good idea. Okay. And maybe you still have a question, so let's draw that figure again about a tube with oil and water. So let's don't draw that in a complicated way. Let's draw in this way and see what's the difference. Okay. Yeah, it works now. So great. All right. So here, we realize that if we apply the same idea, we measure this point, then we'll get the same results, right? That's because we cannot measure in that point, right? Because if d rho dt equals to 0, it means our measurement at that point is go along with the fluid, right? Right, because when we derive this, we know that it's go with the fluid. So actually, or probably. And when the fluid flowed from this direction to here, so the next stop is becoming this way. But because the observer move with, they actually go with the fluid, right? The same function with the fluid. So the density does not change because this function equal to 0. Then you actually get an incompressible fluid, right? Good idea. So if you use capital D, you move with the fluid. If it's incompressible fluid, you get this thing equal to 0. It means it moves with the fluid, but the density does not change. In the previous cases, you don't move with the fluid. You measure at this point. And so the density can change because you may encounter other fluid. But here, you move with the fluid. If it's an incompressible fluid, the density cannot change. All right? Hopefully you get an idea. If you have questions, let me know. Is that clear to you guys? So you get an idea, right? You get the idea is the partial derivative. You only describe the behavior of one fixed point. And in that fixed point, if you use other fluid and flow through that, then you should be and flow through that, then you should detect the density change because you detect the density of different fluid. Nevertheless, if you use this capital D, your observer is go along with the fluid, just like this one. Like this one. You go along with the fluid. And once you go along with the fluid, if the fluid is incompressible, then your density will not change. Or we should say if the density is not changed, does not change, sorry. If the density does not change, the fluid is incompressible. All right? Clear, right? Clear. So that's the difference between the partial derivative and this full derivative with the coordinate that go with the fluid. All right. Now we finish the equation of continuity. So any question of that? The equation of continuity. And if not, at least try to make sure that you understand how to derive the equation of continuity, okay? Just as we say that it's important, very important. And also try to understand how to rewrite the equation of continuity in this capital D. And as we say, that will be one question in the final exam, all right? All right. Okay, let's move on. No. So next, we can continue to do the equation of motion, but I don't want to do that. Let's cancel out. Let's delete the other equations. So we just finished the equation of continuity. Okay. So next we want to deal with the equation of motion. Okay. But if I directly use the force bands to deal with the equation of motion, that's okay. That's definitely okay. But I will encounter some problems because you guys are not familiar with how many forces in the fluid. So I want to first introduce the force in the fluid, okay? It has many different kind of force in the fluid. Yeah. It's not like a solid. Solid, you know, force is in this way. But in fluid, you encounter many different kind of force. As you can see here in the equation, you encounter some force is from the pressure, and some force is from shear stress, and others from gravity, and also some from the movement of the fluid. So I want to introduce all those forces, and then we can do the force balance and then derive the equation of motion. Hopefully that's clear. So let's do that, okay? I remember one thing that real bad. Okay, I will upload all the PowerPoint today, okay? Sorry about that. I forgot to do that. Okay, and the best way to introduce the force is this book, The Transport Phenomena. Oh yeah, we should have a break. So let's have a break, okay? And we'll come back at 9:10, okay? let's come back here. And the funny part is the officer in our department said that machine is not inside here. Nevertheless, when I open this, we get no signal jammed, right? Kind of funny, right? But anyway, let's still try to get some, get our codes done, and then see what will happen to this microphone, okay? And also, during the break, I received 2 questions from your classmate. The first one is talking about incompressible fluid and incompressible flow. And I think his suggestion is meaningful because the incompressible fluid is majority describe the behavior of the fluid. And so when I describe all those behaviors, it would be incompressible flow should be a better word, okay? So I try to correct my mistake. So let me say that because it's a flow, right? And I try to describe the flow behavior. So I should use the incompressible flow. And the incompressible fluid is majority used to describe the stationary fluid, okay? Okay, so first thing is I will in the future use the incompressible flow to describe this behavior. And second thing is, second question is kind of interesting. So one of your classmates come here say that I show this one, okay, this one. For the incompressible flow, this one is not necessarily equal to 0. But here's a question. If this one equal to 0, is it possible it's a compressible flow? So let me say the question again. So your classmate talking about that if this one equal to 0, this one equal to 0, is it possible to be a compressible flow? All right? And let me give you an example, okay? Erase that. Okay, yeah. God, this is so bad. Kind of interesting. So the question is, if this one equal to 0, is it possible to be a compressible flow, okay? All right? And let me give you an example, okay? Probably in that way. Let me seek help from Google, okay? if that many of you notice things. This is what happened in the. Let me use the other figure. You see a rock here, right? And you see the things here. This, and this is actually something like this. Okay, and it will give you the supersonic fluid, a supersonic flow. So how to do that? Let me explain this. You actually have a device in this way, and then in this way. And at the part, the narrowest part, you reach the sonic speed. Not you, the flow reach the sonic speed. So the high pressure here, and here is low pressure. And we put air here. Probably use this one. We put air here. It will be compressed, and reach this point, and then we expand, and then speed up again. So this point, if the fluid. The air, if the flow of the air can reach the sonic speed, then it will become the supersonic flow. Okay? And let's come back here. You have this one, right? So if you observe this, and if the flow is steady flow, so it continue flowing this way. You don't observe the difference of the partial density, partial T, right? This term is equal to 0 when you observe that point. But the flow is definitely a compressible flow. Otherwise, you will not be able to have this supersonic flow. All right? So it's an example to show you that if this one equal to 0, can still be a compressible flow. Okay? Hopefully it's clear. Right. But anyway, if you have no you have no memory about this supersonic nozzle, at least from now on, when you see a rock, you can tell your friends, yeah, we know why the shape is in this way. It will create a supersonic flow. If you are interested, you can go to this book, the maquette. This book. So it seems in chapter, I don't remember which chapter. It's a compressible fluid chapter, and you will see this, and they will have all the equations and show you how the velocity of the fluid can reach the sonic speed and then become supersonic. Okay, all right. Let's come back here. Regarding to this national alert, it's kind of funny that let me tell you one story. It's very interesting. So when I was a grad student, and one day we are in class, and then we get an alert of the tornado. It's so exciting. In all my life, I never have chance to see the real tornado. So everyone go to the base floor, and I was just waiting there and try to see the tornado. Unfortunately, or unfortunately, I didn't have chance to see the tornado, but the cloud is so low that it's the cloud usually is higher than the mountain, right? Or at least higher than our building. But that day the cloud is as low as about third floor. It's very low and it's dark, but there's no tornado anyway. It's kind of interesting experience. All right, let's come back to the BSL. Okay. There are many things I need to introduce before I can introduce the force. So first thing that's let's go step by step, okay? Let's go step by step. First thing is for Newtonian fluid. You remember that, right? We have this figure. This one. And we show that this line is Newtonian fluid, right? So this line, it shows that the velocity gradient and the shear stress, the relationship between these two are linear. It's linear, sorry. It's linear. And if you apply that, you get here the velocity gradient, right? And the shear stress. And the relationship between these two is linear. And the slope is your viscosity. All right. So this is Newtonian fluid. And this is one of the canonical example for the fluid. For flow, okay, for laminar flow. So we try to describe a laminar flow that is between two plates, and the lower plate will move to the right with the velocity of v, and upper plate is fixed. And once we do it that way, we'll have a velocity of the fluid as v on the point contact with the lower plate. Okay, so it's in this way and move in this way, right? And then you will have the velocity gradient dvs dy. Y is in this direction. And shear stress tau wise exists between the plate and the fluid, right? Between the plate and fluid, and is in the dimension. It's in the unit as the pressure. So this movement of the plate will offer a shear stress to the fluid and make the fluid move and then have the velocity gradient, right? That's the idea of that. Okay. And last week we introduced the unit of the viscosity, and it should be okay. I don't want to introduce the viscosity again, but we can have some understanding about shear stress, which is in the same unit as pressure, so it's Pascal. And velocity, okay, should be fine. Viscosity, last week we introduced that. And this is a so-called dynamic viscosity. You only need to know that it should be the viscosity mu. So let me write down, okay? Yeah, sorry. So this is the viscosity divided by the density. That's all. That's all. In this course, we didn't use this frequently, so it's fine. You just need to know that. All right. I need to explain the index of the shear stress. Okay. It's kind of very important because it's kind of important because if you don't know this index, then we will not be able to do any balance. Thinking about that, if we want to do a force balance, we definitely need to know the direction of the force, right? Otherwise, we cannot do a balance. I see, and this shear stress actually have two indexes, so we have to introduce these two indexes. And then we know what's the direction of the force, right? Okay, so I get this figure from the internet, from here. Okay, anyway, so you can think about this shear stress. It has two indexes, and to describe two things. The first thing is the phase it acts on. Okay. So think about that. You have a shear stress, and you need object, so the shear stress can act on that object. So this first index describes that surface, the object. Okay. And the second index is very easy. It indicates the direction of the force. Okay. Let me repeat it again. So the first index is indicated the surface that will receive this shear stress. Okay. And the second index is the direction of the force, because the shear stress is in the unit, is in the same unit as pressure, right? So once you have the surface, you multiply the shear stress with the surface, you get a force, right? And force will have what? The direction. So second index is the direction. The first index is the surface. Nevertheless, some of you may have a question: how can we describe a surface with one index? Okay, so let me show you. Okay. Let's think about equation of the plane, okay? So you have a plane. If you want to describe this plane, what will you do? Okay, you will try to write equation. And some of you know that it can be written in this way, right? The equation for a plane. Nevertheless, if we want to take a close look at this equation, we realize that it's actually derived from this one. From, you assume there's a vector, normal vector. And this normal vector is perpendicular to any vector in the plate. All right? And then we will call this normal vector R. And then we call this point x0, y0, z0. Okay? And so you have any vector and vector on the plane can be described as x probably we use Rn here. Probably I'll give you 2 minutes to take a look at that. The reason I do that is when I was a student, I usually need to think about the things myself instead of directly exposed to the explanation of the instructor. And I feel that is a better way to study. And even nowadays, I still learned from some website course, and then for those courses they use PowerPoint, right? They usually don't write it down, and then so usually they show one PowerPoint. I will just post it, and I will take a look at the equation myself for probably 1 or 2 minutes, so I can understand that, and then I will continue the video. So that's what I do, and I think that's a good way to learn that. So I will do the same thing. Okay. So I will give you some time. If you want to make notes, you can do that. If you don't want to make notes, you just go through that and make sure that you understand it. Okay? Yeah. Kind of funny, right? Let's try the other one and see if this thing can help. Really, right? When we open this, it does not have noise. I don't know why. It's kind of funny, actually. Because they say there's nothing inside here. Kind of funny, actually. Oh, I have some. This one is much better. It does not have that. I don't know if I have a little. Okay, anyway. All right, let's come back here. So if we try to describe a plane, we can easily write down this equation, like I can't believe all of you can write it down. Nevertheless, if we want to fully understand the things, we can use this to explain how we get this equation. So actually there's a normed vector, which means this vector is always perpendicular to any vector on the plane. Okay, so there should be one norm vector for a plane. This is a plane, it's not a curve, okay? So you only have one. Okay, you mean the other direction, that should be fine. But this norm vector, I shouldn't say there's one vector only. I should say there's one direction of the norm vector. Not one direction. Sorry, I made a mistake. I admit it. So we can always find one. We can always find an arbitrary vector that known to the plane. Okay, and if that's the case, let's call this norm vector Rn, as shown here. And this norm vector should have a contact point with the plane. And that contact point, let's assign x0, y0, and z0 to the contact point. And once we have that, we know that this norm vector is perpendicular to any vector on the plane. So we want to take out one arbitrary vector on the plane. And the easy way is we just choose the other points. Perpendicular to your norm vector, right? And if that's the case, the dot product should equal to 0, right? So you have the other vector here. We call it RP. And this RP dot your Rn should equal to 0. And let's assign the Rn be ABC. And RP is easy, right? Because RP, you take any point, any arbitrary point. So it should be x, y, z minus the x0, y0, z0. So you get vector, right? So you get this one as your RP. And then you do a dot product of them. And with some algebraic, you finally get an AX plus by plus cz equal to a x0 plus b y0 plus c z0. And since x0, y0, and z0 is a certain point, it's not arbitrary point like x, y, z, you can assign this whole thing and lump that, and then assign that equal to d, and then you get the equation of the plane. Okay, right? Should be fine. Should be fine. All right. And after we say so much about that, we realize one thing. If we want to describe this plane, okay, this plane, we need two things. One is your Rn, right? The norm vector. And the other is your contact point. Right? Right? And your shear stress here, is use the same concept. It's first index. It's try to indicate that Rn. Okay? But because when we try to write down shear stress, we are not picking up the arbitrary coordinate, but we pick the coordinate in this way, right? The x, y, z. So they are perpendicular to each other. And if we want to describe the YZ plane, the Rn should be x, right? Should be x. So that's why the first index of the shear stress in YZ plane is x. Okay? Hopefully it's clear. And the first index of the xz plane, we want to find the norm, the vector of xz plane. That should be y, right? So the first index is y. Okay, all right. Similarly, for the xy plane, which is this one, your known vector should be z. So the first index is z. Okay, so the first index indicates the surface or the plane this shear stress act on, and that should be use the vector known to this plane, right? And the second index is kind of easy. No one can miss it because it's simply the direction of the force. So think about this shear stress. It acts on the YZ plane, but its direction is in Y direction. Okay, in this plot, we don't care about the sign, okay? So I know Y is in this way, and you plot in that way, but don't care about the positive and negative side. Just that direction, okay, the Y direction. And here, the XZ is the second index indicates the force direction is the S and the Z direction. That is Z direction. And this one, the force direction is the X direction. And what's that mean? That means if you use this shear stress, you multiply by the surface area or the plane area of this YZ plane, the YZ plane. Okay? And you multiply by that, you get a force. And the direction of that force is indicated by the second index S. So for this one, you multiply by the area of this part, you will get a force in S direction. Similarly, for this one, if you multiply by the area in the YZ plane, you will get a force in Y direction. All right? So, any question of that? Or you guys fully understand of this? You guys go in the deeps. Some of you, not all of you, but it looks like half of you are in a deep sleep. That's too bad. Anyway, if let me give you advice. If you cannot understand this, please make sure your classmate understand it and then seek help from them. Okay, okay. Don't just let it go. It will unfortunately also happen. You will also see this in the final exam. Okay, so don't let it go. Make sure you understand it, or you can ask your classmate, or at work situation you can ask me during the break. All right. Okay, so this is the example in BSL. Let's go through this example. So BSL says compute the steady state momentum flux tau y in this unit. When a lower plate velocity v in figure 1.1-1 is 1 feet per second in the position S direction, the plane separator y is 0.001 feet, and the fluid viscosity mu is 0.7 cp. All right. So he tried to deal the example tried to deal with this situation. Okay, you have two plates, and then one moved, the other does not move. And the example specified the velocity of this plane, and also the distance between two plates. All right, good idea. And the viscosity mu. So we know the v and y and also mu, and we want to calculate the shear stress. All right. So how about I write this down? So here. And now let's come back to the example. So in order to get this shear stress, we need to identify this thing, right? dvx dy. Because we already know the viscosity. Viscosity is here, 0.7 cp. So we know this. We want to add it by this thing. And the way to do that is kind of easy because the author just use the velocity gradient. Use the velocity gradient divided by, so use the difference of the velocity divided by the distance of the plates. The velocity difference, the difference of the velocity is you have one plate, we have, so the example, okay. So the example specifies that there is a plate move in velocity of 1 and the other plate is stay there with velocity of 0. So the difference of velocity should be 1, right? Actually minus 1. It depends on the coordinate, okay? Because we choose in this way, right? We choose in this way. Okay? So if you have a higher y, you actually have lower velocity. So that becomes minus 1. Okay. And then the delta y is easy, the distance of two plates. So you put a distance of two plates here, and then you get delta vx, delta y. And you use that delta vx, delta y to put that in here. You put the delta vx, delta y here. You get the vx, dy. And you get this one. And then you have the viscosity, this one. And you do some unit conversion here. Okay. Anyway, you guys know how to do it. And then you put that here. And then you multiply by this one. And finally you get this one. And this is the shear stress. Is that okay for you guys? Okay. And this shear stress, unfortunately, this example is not a very good example. The example asks you to calculate the shear stress, but never tell you what this shear stress means. Okay, this shear stress, if you multiply by the area of the lower plate, so you multiply the area of the lower plate, should be the force you require to move the lower plate if the plate is without weight or any other friction except from the fluid. Okay? Alright? Good idea, right? So the fluid and the plate, and this plate, it requires this shear stress multiplied by the surface area. And that's the force used to compensate or not compensate, to make the fluid flow. Alright? Hopefully it's clear. Let me say again in Chinese. It's kind of important. 这个 tau yx 啊，他虽然叫你算，他没有告诉你 tau y 是什么意思啊。那我觉得这样很糟糕哦，因为你算了，你也是不知道 tau y 是什么意思。不会啦，其实应该很多人你们都知道，因为你们背景是化工的。但是不管了，如果你不是化工的，我解释一下好不好？你这 tau yx 理论上它算出来这 tau yx 应该就是你这个平板，就下面这个板子，它如果再乘以这个板子的面积， 就是 tau x 乘以板的面积，应该就是板子需要的力，然后这个力是用来移动这个流体所需要的力。当然，板子可能自己有重量或者是自己有摩擦力，那我们不管它，那是其他的力。但这个力是用来移动这个流体所需要的力，好不好？那这个力呢，它的方向应该是在 x 方向，所以你的 shear stress 才是 tau yx， 好不好 ？OK。And also we know that the direction of the force should be in the x direction because the shear stress, the index of the shear stress is tau yx, so it's acting on the plane perpendicular to y vector, but the force direction is in x direction. All right. And there's one question here said that what's the shear stress if delta y become 1 feet? Now it's 0.001 feet, and if it become 1 feet, what would be the shear stress? Anyone want to answer that? It's an easy question. You can get easy points, and I like easy points. Yeah, but the one behind you, but yeah, okay. This example is just try to help you have the idea that if two planes is separated, then you need less force to move the fluid. You can think about Oreo, okay? Oreo, you guys know Oreo, right? That funny cookie with some cream between two black cookies. Okay, Oreo has two versions. One is normal Oreo, and the other is double cream Oreo. So you can try to move that. You'll find that the force is different. All right, and by the way, I didn't receive any benefit from Oreo, so you can try other cookies. It doesn't need to be an Oreo, okay? Or you can do that by yourself. You just take two cookies and then put some honey in between, and some with a lot of honey and some with a little honey, and then try to move that. You will feel the force required to move the cookie is different. All right. Here give us some idea about the viscosity of the water and air. And the interesting thing here is for water, if you increase the temperature, the viscosity go down, so decreased, okay? So along with the increase of the temperature, the viscosity decrease, okay? But for the air, the increase of the temperature increase the viscosity, okay? And why they act differently? This is because the liquid, the viscosity is majority come from the interaction between molecules. And let's use the water for example. The water, it has a hydrogen bond. And this hydrogen bond, if you increase the temperature, the effect of the hydrogen bond on the fluid, on the water, will be reduced. and so the viscosity reduced. Okay. Nevertheless, for air, the viscosity majority comes from the collision of two molecules. So if you increase the temperature, you increase the frequency of collision, so you increase the viscosity. All right? And this is just give you some common sense that, okay, for fluid, sorry, not fluid, fluid should be, both of them should call fluid. For liquid, the viscosity usually decreased when temperature increased. And the air is in the opposite direction. If you increase the temperature, usually the viscosity increased, right? And second information we can have is the viscosity of the air is nearly 1% of the fluid at 0 degree. So we know that the fluid, water, sorry. We know that water has much higher viscosity than air, all right? That's the second information we can get from this figure. But for 100 degree, the water only the viscosity of water is roughly tenfold of the air. Okay, the difference is not that huge. All right. Okay. And then this one is the example in BSL. It try to estimate the viscosity, okay? So you write down two equations. Anyway, since this example is in the BSL, we just finish that. Let's go through it. Two equations is these two, okay? One is based on the volume, temperature, and molecular weight, and the other based on the molecular weight, the pressure, and the temperature. Okay. And then we have this example. We have only 2 minutes, 1 minute, so we should not be able to finish that. But okay, we can go through the example and then have a break, and then after a break we'll go through the answers. The example says that you want us to estimate the viscosity of nitrogen at 50 degree, and this pressure is very, very high. Okay, it's very high. And the molecular weight is 28. And critical pressure is only 33.5 atm, so this pressure is real high. And critical temperature is 126.2 K. Okay, I don't know if you guys have an idea about this pressure. It's a kind of a crazy pressure. Give you an example, okay? If you use some high pressure things like HPLC or something, your pressure usually is located at probably 20 to 80 atm, and this is 800. This pressure is so big, even you put a bacteria there, it will be crushed and died. So people use this pressure for food process, so they kill bacteria with real high pressure. Although that kind of things you cannot see much in Taiwan, but if you go to US or Europe, and then you find so many food that they are in like the meat is raw meat, but it will not spoil. It will not spoil quickly because they use this process to kill all the bacteria. Okay, or you maybe see some juice. They also use this process to kill the bacteria. So in that way, they don't need to use heat to kill the bacteria. So it's a very, very high pressure. Okay. Anyway, let's have a break, and we'll come back at 11:10. Okay, let's continue the course. So we have the equations, this one, right? This one. And then we put this one here. And then the author want to get viscosity. The way to get viscosity is he first calculated the critical viscosity, okay? And then he used this diagram to get the relationship between the critical viscosity and viscosity. All right. So first thing we need to get a critical viscosity. For this example, it's kind of easy, right? Because it gives us all the information. So the way to do that is we put the equation here, and then we try to substitute all the values into those variables. So the M should be 28, and PC should be 33.5, and TC is 126.2. You put that here, and then you get a critical viscosity. So this one, so this one, and then you want to get the relationship between the critical viscosity and the viscosity. But in order to get that, you need two informations. One is the PR, the P divided by PC, the critical pressure, and the other is TR, T divided by TC. So let's do that. So TR is the temperature divided by the critical temperature, right? So the temperature given here is 50 degrees, so you have 50 and plus 273, so you get K. And TC is given here, so you put TC here, you get TR here. Pressure, you get pressure here, and PC is here, so you get a PR here. So PR is, let me write down. Okay? So we have PR, and TR. Okay, then let's try to get a UR from the figure, okay? So, yeah, 25.5. Something here, okay? Something here. Probably I just sit here. That's a better way. Use this. So PR should be this line, this curve, okay? And you have TR 2.5 says 2.5 says somewhere here, and this curve, and finally we get something here, 2 point something for the UR. So he find the UR is 2.39, which is pretty close to what we get. And hence the predicted value of viscosity is this one, UC, this UC, multiplied by the UR, and get U, right? So UC multiplied by UR, get a U. So the measure value is from some literature, okay? We cannot get a measure value, okay? It's from literature, it's not from the equation. And then he said this is close enough, all right? Okay, great. So next thing, we now have the position to introduce the shear stress. So we know we can have the understanding of about different kind of, not shear stress. So we can have understanding of about a different kind of force. And the first thing should be the shear stress, okay, the tau. And since the shear stress is the same as the pressure, so we in the BSL usually they put two together, and then call the combination of two the molecular stress. why they call it molecular stress. All right, let me explain this, okay? So, when you have a fluid, some fluid here, okay? You encounter the two force. One is from the pressure, so it has a pressure, okay, known to this fluid, right? And the second is shear stress. If we have the air flowing this way, so it has some shear stress in this direction, okay? All right. And think about all those force is in the molecular level, right? The pressure is transport, or should I say transport, or pass. It's passed by the molecular force, right? And shear stress also, as we say at the previous slides, in liquid, for water, the shear stress can pass through hydrogen bond, right? So it's molecular way. And some force is not come from the molecular way, okay? It's not come from the molecular. So this one, they all come from the interaction between molecules. So they call the molecular stress, as you can see here. And some other forces come from this way. For example, we have a droplet here, but we have the other droplet here, and this droplet just bump into this droplet. It will cause the force, right? Just bump in. It will cause the force. And this actually is the one that you see in the equation of motion that Low V returns. And we will explain that later, okay? So first, let's explain the molecular stress. So basically, you can think about that. It has two kinds of force. One is molecular force. So this force is come from the interaction of molecules. And the other is convection part. It's directly from the other fluid that just flow in, okay? All right. And also here, let me say something here. I know you guys know the delta function, but please make sure that there's two delta functions. One is this so-called Kronecker delta, and here is the Kronecker delta. Kronecker delta is the I and J is discrete. Discrete means means discrete. I don't know how to say that. It's not continuous function. It's a discrete number. Okay, all right. And you have other delta functions that usually we don't use that in this course. We usually use this Kronecker delta. Okay. I should have a slide to introduce that two delta function. Okay, anyway, if we encounter that slides in the future, that I'll show you, okay? Anyway, this is Kronecker delta. All right. It's a discrete function, so your I and J can be X, Y, or Z only. You cannot be something between X and Y or something between Y and Z. Okay, so it's discrete. And this delta function gives you very interesting results. If you put that here, you realize that for the pressure, the first index indicate the plate, right? The plate. So the first index is the vector that perpendicular to the plate. So you get the first index that perpendicular to the plate. And for example here, and then that perpendicular to the plate. So you get the first index. And the second index is the direction. And interesting, the direction is in the same direction of the first index, right? And that gives you perpendicular to the plate. So direction also perpendicular to the plate. And that's the pressure, right? Pressure is always perpendicular to your to the surface of the liquid, right? So this one describes the important feature of pressure, okay? Because the first index and second index should be the same. You use the delta function to force them the same. So the first index, as we show here, if you have a plate here, or probably you can think about in this way, you have and then you have a liquid surface here, right? So you think about that liquid surface here. And the first index is perpendicular to this liquid surface. And second index is the same one, so it means that the force of the pressure is always perpendicular to the surface. Alright? Hopefully it's clear. And then I don't know why the BSL, the author of BSL, use pi, since pi is kind of fixed things to us. But anyway, we show our respect to his notation. Okay, so we use pi, still use pi. Okay. It has some explanation of this. We can go through that. So the first explanation is say that this is a force in the z direction. It's important. It's in the z direction, and on a unit area perpendicular to the I direction. So this is the area that the force worked on. Okay. So force has one direction, and force should work on some area. So this is the area, and it's perpendicular to I direction. Where it is understood that the fluid in the region of less xi is exceeding the force on the fluid of the greater xi. So you think about that is you have two fluid and you have the force pass by, all right? And the second explanation of that is a flux of, let's say, momentum in a positive I direction. So the second one, they try to use the momentum to describe this. And that is from the region of the less SI to that of the greater SI. Okay. All right, should be fine. And know that this pi, the molecular stress, is a tensor. So it should have 9 components. Kind of easy to understand that, right? Because you have 2 indexes, right? You have 2 indexes. And the first index can be XYZ. The second index can be XYZ. So total you have 3 multiplied by 3. So you have 9 components. So 9 components here. All right. I know that because the pressure is always perpendicular to your fluid. So you have pressure only at the pi xx, pi yy, and pi zz. And for other position, you only have shear stress. You don't have pressure. Kind of easy, right? No problem at all. And this one is from the index of the BSL. It tries to describe the shear stress, the relationship between shear stress and the velocity gradient. I know in the previous example it looks so easy, but in reality it's not in that way. You will have the shear stress and gradient of the velocity gradient in this way, not in that simple way, okay? But of course, this one can reduce to that simple way, all right? And if we are dealing with incompressible flow, we'll get this divergent V equal to 0. And so we'll get rid of this term, or this term. All right. And we have this term. And we can also write this term in a vector form. It can be written in this way. Tau should equal to, it's not vector form, it should be the tensor form. Tau equal to minus mu. And this is not divergent V, okay? This is not divergent V, it's del V. It's not divergent V. Divergent V is you do a dot product things, so you actually get a scalar. But this thing will give you the tensor, second order tensor. So it's del V plus del V transpose. You just think about that like a matrix, okay? We will come back to this in the future. In the future, you will feel this kind of things is easy. So I don't want to spend too much time on this one, okay? But I know you have a question. What's that del V? Why is not divergent V? How about in this way? I will soon explain this. And you can think about that thing is actually very close to this one, right? You actually have 2V, right? And you don't put a dot product there. So it's okay, you can put 2V there and become a second order tensor. Alright? So if you apply the same idea to this del V, you get a second order tensor, right? No problem at all. So think about that. We can have two vector and then get a second order tensor. Alright? And I will show you that when we introduce the low VV. So don't worry about this del V. Okay, good. And here is the direction of shear stress. It's actually the same as this one, okay? Similar, I shouldn't say similar to this one. We just try to let you have the visual feeling about the shear stress. Okay, so in this one we know the shear stress. This is tau SS, and in this one we know that this one the first index should be R, right? Because it's perpendicular to R. And second index is in theta direction. Theta is go around. So it's R theta. Alright? And for this one, not this one, for this one. For this one, the first index should be R because it's perpendicular to R direction. But the second index should be Z direction. So tau RZ. Okay? Okay. And let's take a look at the sphere. The first index should be R, and second index is theta, and this second index is phi. No problem at all, right? Theta is going this way, phi is going this way. And for this one, we know the first index is kind of tricky, but it should perpendicular to theta, right? Because theta is going this way, so it's perpendicular to theta. And its direction is to Z direction, so it's theta Z. And if it go in this way, let me show you. If instead of going this way, but it go in this way, then it should be theta R. So this is tau theta R. Okay? All right? Good idea, right? Good idea. Okay. Okay. And this is And this is the shear stress for the cylindrical coordinate. But we actually don't use that, okay? I shouldn't say don't use, but we don't use that frequently, okay? And this one, probably we don't use that at all. Okay, the spherical coordinate. Right. If you want to get all those things, you just go to appendix of the book. And also the PowerPoint file, I will upload that. I'm sorry about that. I should upload that before today. There's too many things to worry about, so. Okay. Sorry, here, this one. Okay, that's good. This one, try to explain how the low VV come from. Many of you know that low VV from the equation of motion. Let's take a look at that. So the idea is in this way. You put some plate, okay, some plate to separate the control volume into two parts. And you know, okay, you know the one past this plate, it should have the flow of the liquid in this way. Let me write down, okay, because that low Vx is not clear enough. first of all, we know that the fluid, the volumetric flow through this interface is the velocity Vs multiplied by delta Y delta Z, right? If the length and the height of this one should be delta Y and delta Z. Okay? And then if that's the case, the mass flow rate should be the density multiplied by the volumetric flow rate. Okay? And we know that the force from Newton's second law is the dmv dt. I know you guys know it's you guys you're right in this way, but it's not in this way, okay? It's not in this way. That's for the solid. If you try to write that for liquid, you don't write in this way because this thing, this. And you take up this part and neglect this one. But nevertheless, in fluid, especially for the stationary flow, you actually does not have the velocity change, but have the mass change, right? Because mass go in. So you have the mass change. Okay? So you don't have this term, which is give you the MA, but you don't have this term. And you have this term because the fluid is flow always in that way. So you don't have a velocity change, but you have the mass change. So you put your mass change, dm dt is your mass flow rate, right? So it's this term multiplied by what? By v. Nevertheless, we should think about this f has all directions, right? So v also has. So it's this. It's not a scalar. It's a vector. It has all directions. Okay, and I give you this low VV. Here, this one. But you will say, no, you still have delta Z, delta Y. Okay, think about that. If you have a shear stress that causes the force on this plate, you will have your shear stress multiplied by delta S, delta Y, right? So since you want to put this thing together with your shear stress, the molecular stress, so you want to get the same unit, right? So you divide by delta S, delta Y, and delta Z, delta Y. So finally you get this. You get this. Okay? Good idea. Clear to you guys? Clear. Similarly, you should let me have a drink. Oh yeah, sorry. And wait for some people who need to make notes. So for the one who make notes, you can just make a note. And I'll go through that again for the people who does not have a chance to catch it the first time. So for this one, if we take the plane in this way, we know the volumetric flow rate through this plane should be the first one, the Vs, and multiplied by delta Y delta Z. And that gives us the mass flow rate, should equal to the second equation with the density here. And if we deal with like a water or something, so we have this, right? And we want to get the force of this one. I mean, it will flow from one side to the other side. It definitely causes the force to the other side, right? You flow in. If you cannot imagine that, you think about a situation. I cannot say you go home and your children run to you. How about in the other way? You go home and you have a cute puppy. Puppy is dog, right? And then the puppy run to you, and the puppy jump to you. Definitely you will receive the force from the puppy, right? Okay, so it's the same thing. The flow jump into the other flow. It causes a force. Okay, so it has a mass flow, but how to calculate the cause? So we use Newton's second law. Newton's second law is dmv dt, not F等于ma, okay? not in that way. And that should equal to m dv dt. This term is ma. Nevertheless, if we let the flow is a stationary flow, or static flow, not stationary, static flow, I'm sorry about it. The static flow, then you don't have the dv dt, right? So you don't have this term. But you have this dm dt because the mass continue flowing. So you have dm dt. And your dm dt should be your mass flow rate, right? So the only thing you need to get a force is the only thing you need to do is multiply this mass flow rate by the velocity. So you multiply that by velocity. However, you want to put this thing together in balance with your molecular stress. And this, the unit of molecular stress, is the unit of the pressure. So you divide by the area, and then you get this low VSV. And that is this low VSV. All right? I can't believe this time is clear. Hopefully. All right. And once we have that, then we put, And here also we know that this thing, the low V, it also have 9 components, right? The first component, similar to the shear stress, describe the surface. So it's this surface. That's the first component. And the second component is the direction of the force. We are trying to calculate the force, right? The second direction, the second index is the index of this one. Indicate the direction of force. It can be understood, right? Because we use this equation, right? And your dm dt should not have the direction, right? You just, it's a scalar, right? M does not have direction. So the direction is depend on the velocity v. So it depends on this v. So the direction of the force is on this v. And so the direction of the force is on this v. Okay, get the idea? And also this one illustrates that you can put 2 vectors. So the first vector is, so if you write this thing in a tensor form, you actually write this way, right? So the first V is a vector, second V is also a vector. And that explains that we can write del V. All right? That will give us just like this one. Is that clear to you guys? Before that, we deal with this one, right? We have this one. And I say it's not direction V, it's del V. It does not have dot product. And at that time, you may have a question because you are not familiar with this. But once we write the low VV in this way, you understand that that thing is actually similar to this one only. It's nothing more. It's kind of easy, right? You have 2V there, and you get a tensor. Just like what what's shown in the slides, low VSBS, low VRVI. This one. All right? Hopefully it's clear. Okay. Then we combine all of them, okay? We combine all of them. So we have our molecular stress and our low VV here, low VV. So we have this one. And molecular stress can be separated to the pressure, shear stress, and low VV. Not low VV, sorry. Shear stress and pressure. And low VV is from the convection, okay? So we have these three terms. And of course, this phi is a tensor. Since shear stress is already a tensor, right? So phi is a tensor. And phi can be written in two ways. One is with the pressure, if two indexes are the same. So you will have pressure. If two indexes is not the same, we don't have a pressure because this delta function, right? Okay. And here they didn't write down the right. Y pi. Sorry, they didn't write down the phi, but anyway, you know how to write it down. Okay. So it has 9 components for this phi. So any question about this part? Always remember that the first index indicates the surface, and the second index indicates the direction of the force. All right? All right. And once we have this, we can simply multiply by the surface area and get a force from phi, right? Okay. And if that's the case, then we can do the force balance. And in BSL, they call some kind of spatial force balance as shear balance because they take the control volume as a shear. So shear balance is nothing different from the force balance. It's just because they take a control volume of a shear. So they call shear balance. It's actually a simplified situation. If you don't take a control volume as a shear, you may take a control volume for all the directions. And then you can get an equation for general use. Is that okay? Okay. So I have 10 minutes, but I kind of feel you guys are falling asleep. Any question about this? No? Okay. And if you try to do the force balance, you need to, it doesn't matter you do a shear balance or you do a force balance for any control value. You need to take care about the force from the gravity, right? Force of the gravity. Okay? Force of the gravity. And the force from the convection transporter, which is low VV. And the force comes from the molecular transporter. So that pi with shear stress and pressure. Alright? And with this, you can do the force balance. And we can do it in two ways. One is we can directly use this to get the equation of motion. Because we take a control volume in this way. In this way. In all directions. And second way is we don't take control volume in all directions. We only take a control volume in the direction we are interested in. And that's shear balance. So shear balance is actually the reduce the model of the equation of motion. Because the equation of motion will take the control volume for all directions. But shear balance, you only take a control volume for the direction you are interested in. All right? I don't want to go further because I feel kind of tired. But I want to say some funny story to challenge your logic, okay? So, but before that, anyone want to have any question about what we are talking about? Okay, now erase all of them, okay? Let me say something interesting. At least I feel interesting. If you don't feel interesting, you can just ignore it. Okay. So I heard that one faculty in the entrance exam, they asked the student a funny question. He asked the student, do you believe there is a ghost? And then the student is totally crushed, thinking about how can he ask this kind of question. I don't know if you encounter this question, what kind of response you will have. I say this is because this is grade school. When you encounter some question, don't think in a conventional way. Okay, don't think in conventional way. You can deal with the question with your logic. So the first thing is, this question is kind of funny because believe or not is not a scientific description. Okay, this is the first thing. And second thing is, we can prove there is a ghost, but we cannot prove there is no ghost. Right? The scientific prove something exists, but you cannot prove something does not exist. You guys know the idea of that, right? No? Your face show no. Okay, let me say in this way. 200 years ago, if you tell people there's a DNA inside a cell, all people will feel you are crazy. Because they cannot observe the DNA. They can only observe a cell. So they can prove there is a cell, but they cannot prove there is no DNA. Okay? It cannot prove something not exists. Some science can only prove something exists. I use this example is one reason is because we are all tired, and second reason is I want you to feel that for any question in your life, you can always approach with a scientific approach. Okay, scientific method. So, and that question is kind of funny, really. When I heard that someone asked a student in the entrance exam, that's crazy. That's crazy, really. Okay. So next week we will try to deal with the Chopin's in this one. So it's a canonical. So it has a liquid continue flowing here, and then we have a ramp. So liquid will go down the ramp. And the way to the goal for this example is to get the velocity distribution of this small film. And we will take the control volume only in the x direction because we are interested in x direction only. Okay. But how about before we do this, we try to derive the equation of continuity? I think that would be a better way. Because if I do this, you may feel it's difficult. But if I derive the equation of continuity with this control value, then after that you feel this thing is kind of easy. Okay, so next week we will first derive the equation of motion by this one, and then we deal with this example. And we have many examples for the Chopin, so we will go through all of them. And since it's less than 3 minutes, if you don't have a question, let's call it a day. And next week we still have makeup course at 7:40, but majority we will use the video. Since I have already introduced the population-based model, so the video will give you a better understanding about how to formulate the model. All right. So if you want to come, you can come. But if you don't want to come, you can come at 8:10. Okay. See you next week.